All right, let's get started. We are going to talk about polygons today, and something I mentioned last week is when mathematicians talk in terms of definitions, we have to make sure we know what something is before we can use that word. And so I'm going to do that a little bit backwards, but just for a very short time here on this one page. What a polygon is it is a simple closed figure made up of line segments. Those two words, simple and closed, we haven't defined those yet. So we're not really allowed to say that a polygon is a simple closed figure until we know what simple means, until we know what closed means. So let's go ahead and address that right now. What simple means is that the figure does not intersect itself. For example, if I were to draw this shape right here, you could say, but it intersects itself right there where it ends. That's not what this means. That would be a simple figure because it doesn't intersect itself. If instead we were to do something like this, now it intersects itself and we do not have a simple figure. So this is not simple, while the one above is simple. Closed. Closed means that it starts and ends at the same point. So, for example, a closed figure could be like this one right here. It starts and ends at the same point. Something that doesn't start and end at the same point might be something like that. So this one is not closed. Kind of closed is very visual. You can kind of see it. Well, you know, when I look at this one, it's kind of open right here. Yeah, it sure is. And that's a way that we can say that it is not closed because it doesn't start and end at the same point. It doesn't close itself off. So simple means it does not intersect itself. Closed means it starts and ends at the same point. And so now we can define a polygon as a simple closed figure made of line segments. We haven't talked about that line segments part yet. The reason we mention line segments is because that right there, that circle, you could argue, well, that's simple, starts and ends, or it doesn't intersect itself. It's closed, starts and ends at the same point. Wouldn't that be a polygon? No, because this circle is not made of line segments. So this circle is not a polygon. That's just a curve. There's no line segments involved. So that's not a polygon. Any questions on the definitions simple, closed, or polygon? All right. Here's some common polygons. You probably know the names to a lot of these already, but just as a reminder, the names of these polygons are kind of tied to the number of sides that it has. Triangle is made up of 3 sides, and not every triangle looks like that, but that is a sample triangle. Quadrilateral, the prefix quad probably gives you some indication here that that's 4 sides, and this is a sample quadrilateral. Not all of them look like that, but that is one. And we just continue from here. A pentagon has 5 sides. A hexagon has 6 sides. An octagon has 8 sides. Then we get into a couple you probably aren't familiar with, but that's okay. A nonagon has 9 sides, and a decagon has 10 sides. And you can see that decagon's already getting kind of hard to write. Once you get beyond 10 sides, they get harder and harder and harder to draw. I will say once we get past decagon, our creativity kind of goes out the window a little bit. If we had like a 14-sided figure, we would just call it a 14gon. If we had a 22-sided figure, we'd just call it a 22gon. So these Latin prefixes work really well. Once we get to 10, we kind of let those go. We do a duodecagon is 12, but that's pretty unusual to really come across. Otherwise, we've got, you know, just tack gon at the end of the number of sides, and you've got it named. I do want to indicate today also, the main ones we're going to focus on are triangles and quadrilaterals. That's where we're going to spend most of our time and energy. A couple of other words related to polygons are concave and convex. And we want to make sure we know the difference between those. And we're going to talk about this two different ways. We're going to talk about the formal definition, and then we're going to sort of do a more informal way that most people tend to remember pretty well. Formally, a polygon is convex if the line segment containing any 2 points lies entirely within the polygon. Wow, that's formal, all right. Well, let's take a look at this. A line segment containing any 2 points is entirely within the polygon. So that's when it's convex. So let's look at our examples of convex. If I've got a point here and a point here and I connect them, that line is entirely within the polygon. And that's going to be true for every one of these convex figures over here. When I connect those points, my line stays entirely within the polygon. Once I go to a different kind of a figure that we're going to call concave, now it's possible for me to connect dots with a line that's outside the polygon. And so that's how I can tell for sure that it's concave. And all I need is one. If there's one line I can draw connecting 2 points that goes outside the figure, then we say it's concave. And so that's the formal definition. Informally, basically, you can kind of look at a figure and see that concave is kind of caved in. You know, you kind of look right here, it's caved in, it's caved in, it's caved in, it's caved in on both sides. And so that's an informal way to talk about concave. Could be really good with younger students to use that approach rather than the more formal definition. Although I like the idea of using the formal definition with kids, because if they can learn to read mathematical statements like this, that can be really valuable going forward. Are there any questions on convex and concave? All right. Hang on, let me wait just a minute here. Okay, if you're sure. You can ask it if you want to, Jalen. That's fine. I saw you were typing something there. I don't want to just kind of charge ahead. Types of quadrilaterals. Remember, quadrilaterals are four-sided polygons. So that tells us something about them. That tells us that they are simple, closed, made up of line segments. And the fact that they're quadrilaterals means there's four sides. So let's talk through these here. A trapezoid. A trapezoid has at least one pair of opposite sides that are parallel to each other. If we look at this figure over here on the right, we can see that the top and the bottom are parallel to each other. That's all it takes to qualify this as a trapezoid, is at least one pair of opposite sides are parallel, and the top and bottom are opposite. The left and right here are opposite each other, but those are not parallel. So I don't have both pairs of opposite sides parallel, but I don't need both. I only need at least one side of opposite sides to be parallel to be a trapezoid. Top and bottom are parallel, so we can call that a trapezoid. Parallelogram. To be a parallelogram, what a figure has to have is both pairs of opposite sides have to be parallel. So when we look at our parallelogram over there, the top and the bottom are parallel, the left and the right are also parallel. So what that means is that in that figure we have both pairs of opposite sides are parallel, and that's what makes it a parallelogram. Top and bottom parallel, left and right parallel, okay, that's a parallelogram. Now a figure that you're probably fairly familiar with is a rectangle. And a rectangle has all angles are 90 degrees. Now it has to be a quadrilateral first. So, you know, it's going to have four sides and it's a polygon, but also, we're going to throw in this condition that all the angles have to be 90 degrees. So we have 90-degree angles in all four corners. That's what makes this a rectangle. Next up, we have a rhombus. A rhombus is one that's always lumped in with these, trapezoid, parallelogram, rectangle, square. Rhombus is a part of this, but we don't talk about those very much. What a rhombus is all sides are equal in length. So in a rectangle, all the angles are equal to each other. In a rhombus, all the sides are equal to each other. And the way we can indicate that on this picture is by putting a tick mark here, 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 and here. Because there's one tick mark on those, that lets us know that they're all the same length. What if they're not all the same length? How do the tick mark work then? That's a great question. Well, these two would be the same as each other, so we put one tick mark, and then top and bottom in that rectangle are the same, so we could put two tick marks there and two tick marks there to indicate top and bottom are the same. That's why they each have two tick marks. Left and right are the same. That's why they each have one tick mark. And so that's how those tick mark works. Key in a rhombus, all the sides are equal in length. Then we get to a square down here at the bottom. In a square, you're probably familiar with, but all sides are equal in length and all the angles measure 90 degrees. So it has to be both of those things. The sides are equal and the angles are 90 degrees. So in a square, all four angles are 90 degrees and all four sides are the same length. Very specific about that square. Finally, at the bottom here, and I don't have a picture of this one, I'll draw it, is the idea of a kite. And a kite is going to look exactly like you would expect it to. A picture of a kite is going to look like this. Obviously, it can be oriented differently, but that's a kite. And in a kite, two pairs of adjacent sides are congruent. Ooh, there's some words in there. Okay, congruent means they're the same length when we're talking about sides. If we were talking about angles, they would have the same angle measure. But since we're talking about sides being congruent, they're going to be the same length. And I need, okay, let me read this again. I need two pairs. Well, there's only four sides in this thing. A kite's a quadrilateral, so there's only four sides. So two pairs of adjacent, which means next to each other. Okay, so two pairs of sides that are next to each other have to be congruent. All right, well, this pair, oh, sorry about that. Now I've done it. This pair here at the top of this particular kite, those two are congruent to each other. And down on the bottom, these two are congruent to each other. And so let me reread that definition one more time. Two pairs of adjacent sides are congruent. Okay, well, these two sides are adjacent. So that's one pair of adjacent sides that are congruent. This pair of adjacent sides, they're next to each other. They have the same length. So that's one pair of adjacent sides that are congruent. And then I need the same thing to happen on the top. And sure enough, I have another pair of adjacent sides that are congruent. So I have two pairs of sides that are next to each other that have the same length. And that's what makes that a kite. Before we go forward and kind of see, okay, a whole lot of definitions here. What are we going to do with this? I want to point out about the relationships between these. That's kind of where my questions are going to come from, is the relationships between all these definitions of these different types of quadrilaterals. What I mean by that is, when I look at this square down here, I don't really think of it in these terms very much, but this square is a parallelogram. Because, well, to be a parallelogram, both pairs of opposite sides are parallel. Top and bottom are parallel, left and right are parallel. Yeah, you're right. That square is a very special type of parallelogram where all sides are equal, all angles are 90 degrees. But that relationship exists. That, okay, if I have something that is a square, then by definition it is a parallelogram. A way I like to say this is, if I have a Dalmatian, that's a very specific type of dog, but it absolutely is a dog. And that's what's going on here. This square is a very specific type of parallelogram, but sure enough, it is a parallelogram. How many questions on that? Anything on this page that we've talked about? Definitions? We'll do some practice with the relationships, I promise. All right, fantastic. So here's the relationships types of questions I want to make sure that you see. And these are true or false. At first glance, true or false, how hard could it be? Worst case, I'll just guess. Well, I hope that's not how you go into this at all. There's an approach that I want you to take as far as these quadrilateral relationships are concerned. This statement at the top here, statement, let's call it number 1, says all rectangles are parallelograms. And basically, this is just a true or false question. The way that I want, and many of you may be able to answer this already, but rather than that, I want to talk about how I want you to go about answering a question like this. In math, if we are going to say that something is true, it has to be true always with no exceptions. In conversational language, it's perfectly fine for you to say, it's always sunny in Las Vegas. But mathematically, that's not true because, on December 18th, 2004, it was raining. I don't know if that's true or not, but just as an example, you could find a day where it was raining, and that totally wrecks the idea that it's always sunny in Las Vegas. Always has to mean every single time, no exceptions. True means every single time, no exceptions. So the way we're going to approach these is we are going to look and see if we can find a counterexample. If I can find one counterexample, then I can say false. Proving things that are true, we're not really going to go through an extensive process of that. What I'll tell you is what happens is as we try to find a counterexample, we might convince ourselves that it's true. Here's what I mean. All rectangles are parallelograms. So as I approach this problem, I'm trying to find a counterexample. So I'm going to see if I can draw a rectangle that is not a parallelogram. All right, well, let's see. I'll draw myself a rectangle here. All right. I want to find a rectangle that's not a parallelogram. Well, parallelogram means that both pairs of opposite sides are parallel. Yeah, okay, so that one didn't work. That rectangle doesn't work as a counterexample. That one is a parallelogram. Well, what if I draw a rectangle this direction then and maybe make it wider? Okay, let's see. Is that not a parallel? Left and right are parallel. You know what? As I work to find a counterexample, I convince myself. Every rectangle I draw is going to be a parallelogram. So the question here, the idea here that all rectangles are parallelograms, that statement is true. I can't find a counterexample. You don't have to prove that it's true. You just have to get convinced that it's true. And an easy way to do that is kind of go down the path of looking for a counterexample. Now we'll look at the one at the bottom down here. All rhombuses are squares. Okay, all rhombuses are squares. My approach to this true or false question is to see if I can find a counterexample. All rhombuses are squares. Could I draw a rhombus that's not a square? Is how I'm going to try this. Well, I could draw a rhombus that looks like just sort of your standard rhombus. All 4 sides are the same length, so that's a rhombus. That's not a square. A square has to have 90-degree angles. So right here, this is my counterexample. And I can definitively say that this statement is false. All rhombuses are squares? No, they're not. Look at this one right here. That's a rhombus, it's not a square, so that statement is false. Do you have any questions about either of those before I have you try a couple? All right, here goes. So 2 statements on the page. I'm going to set up a poll. Every trapezoid is a parallelogram. And then the second one is all squares are rhombuses. So those are our two statements there, and I'll set up a poll with this so you can answer true or false. The first one listed is the statement at the top of the page, every trapezoid is a parallelogram. The second one listed is the statement at the bottom of the page, all squares are rhombuses. And you just decide true or false on each of those and then pick the appropriate response. Our first instinct is that true or false questions are going to be easy. As it turns out, these, I don't think they're easy. You know, we really kind of have to think about it. I tend to work through the, can I find a counterexample? And in that process, do I convince myself that it's true process rather than going on sort of a gut reaction or a gut instinct? Some particular questions might come across as easier to you than others, and that's perfectly reasonable. You might read one right away and go, oh, well, obviously that's true, or obviously that's false. But working through the process of a counterexample can be really effective too. All right, let's take a look and see how we did on this one. Okay, not unanimous, but strong agreement. That's a good place to be, and hopefully we'll clear up any misunderstandings that might be in place. All right, so for this first one here, we are looking at this from a standpoint of, can I find a counterexample? It says every trapezoid is a parallelogram. So what I want to try to do is draw a trapezoid, at least one pair of opposite sides parallel, that is not a parallelogram. That's how I'm going to try to solve this. And so I do a trapezoid, and I say, well, if I do a trapezoid like this, then in that picture, I've got one pair of opposite sides parallel, but the other side is not. So that does qualify as a trapezoid. Yes, it is a trapezoid. But is it a parallelogram? Well, to be a parallelogram, I need both pairs of opposite sides to be parallel. Top and bottom are, but left and right are not. So right here, that purple shape in there, that is a trapezoid that's not a parallelogram. So the idea that every trapezoid is a parallelogram, well, no, it's not. That statement's false, and right here is my argument. Well, it's tucked away very tightly in there, that purple trapezoid that's in there that has at least one pair of opposite sides parallel, but it does not have both pairs of opposite sides parallel. One thing I want to say about when you investigate these types of problems, because this may be a new idea for you, is what if you drew your trapezoid this way and said, well, right there, that has at least one pair of opposite sides as parallel. That's all it takes to be a trapezoid. So this picture is a trapezoid, and it's also a parallelogram. And that would be true. What we found is, well, here, there is a trapezoid that's a parallelogram, but that's not what the statement said. The statement said every trapezoid is a parallelogram. You might be able to find one. Sure, that's a trapezoid. That's also a parallelogram. But this says every, which means I'll never find an exception anywhere. And since I was able to find this exception, then I have to say that that statement is false. So the existence of one doesn't make it true that every trapezoid is a parallelogram. The existence of one counterexample does make it false, though. Let me know if you have any questions on that. And we all went true on the bottom one, so that's going to be simpler. All squares are rhombuses. All right, so I'm going to try to draw a square that's not a rhombus. So here's my square with all four sides the same and all four angles the same. Is that a rhombus? Yeah, it sure is, because it has all four sides the same, so that's a rhombus. All right, well, let me try to draw a bigger square then. Let's see if that does it. All four sides the same. Hey, wait a minute. As soon as all four sides are the same, that qualifies as a rhombus. So you know what? Every square I draw, no matter what, if it's a square, it's going to be a rhombus, and that's going to be true. Let me know if you have any questions about anything with the definitions of those quadrilaterals and the relationships between them. True-false questions are my favorite for these. Outstanding. Okay. I mentioned that as far as those polygons were concerned, that quadrilaterals and triangles were going to be the most important for us. We talked a lot about quadrilaterals just a minute ago. Now we're going to talk about triangles. Kind of the same idea. We're going to go through all these names of different triangles and talk about what those names represent. So the first triangle we have here is equilateral, and that means that all sides are equal and all angles are equal. So in this equilateral triangle here, all the sides are equal and all the angles are equal. One thing I want to just sort of throw out there, and if you remember it, great, but if you don't, that's okay. If I get to do the sum of the angles of a triangle, if I add up the angles of a triangle, what do I get? Anybody remember? Hey, that's awesome, Summer and Jalen. Very good. 180 degrees. And so what that means is if I have this equilateral triangle, then all the angles in there have to be 60 degrees. Each one of them is going to be 60 degrees because they all have to be equal and they have to add up to 180. Just something to sort of file away to remember. Okay. Up next, we have an isosceles triangle where at least two sides are equal. And in this picture over here, we can see that it's those two sides that are equal to each other. A key word there is at least, because that creates a relationship between equilateral and isosceles that I'll just kind of leave laying there for right now. We can talk about it more if we need to, but at least two sides are equal. That's an isosceles triangle. And so far, we've talked about the idea that all of the sides are equal, at least two of the sides are equal. The only thing left as far as the sides are concerned is none of the sides are equal, and that's called scalene, when none of the sides are the same length. What we've done here is we've put these triangles in different categories based on their side lengths. We can have all three sides the same, at least two sides the same, or no sides the same. And the names that go with those are equilateral, isosceles, and scalene. On the bottom half of this, instead of side lengths, we're going to talk about angle measures. Now let's see. A right triangle has one of the angles measures 90 degrees, and we can see that's the one right there. Just sort of a side question. Would it be possible to have two 90-degree angles in a triangle? Jalen says no. Why not? And there's different ways you can answer this. It doesn't have to be elegant or perfectly written. I just kind of want you to tell me why we can't have two 90-degree angles in a triangle. Perfect, Jalen. I was good with the first thing, but being extremely precise with that language is excellent. I like it. And so 290 degrees would already be 180. If you're just looking at the numbers, you could say, well, if I have a 90-degree angle and then I add another 90-degree angle, there aren't any degrees left for the third angle. So I can't have one. So this doesn't work strictly by looking at the numbers. Another way is some of you might do this more visually and say, well, if I try to draw it, if I put a 90-degree angle over here and I put a 90-degree angle over here, hey, wait a minute, that's not a triangle, it's a quadrilateral. Well, that's not going to work then. I guess I'm convinced you cannot have more than one 90-degree angle in a triangle. And that's why we start out with saying that there is one 90-degree angle, because you can't have two. It wouldn't work. An acute triangle, all the angles are less than 90 degrees. So if we look at those three angles there, they're all less than 90 degrees. They have to add up to 180, but they're all less than 90 degrees. And it's a little corny, but an easy way to remember this is the angles are all small, so they're all acute angles. I apologize in advance. It's just an easy way to remember it. Finally, an obtuse triangle is we have one angle that's greater than 90, like this one right here. That's bigger than 90. That makes for an obtuse triangle. It's an obtuse angle, and it makes an obtuse triangle. So we can categorize these triangles based on side lengths and also based on angle measures. We're going to do the same kind of thing with triangles that we did with quadrilaterals as far as the relationships are concerned. So let's take a look at what we can do with questions involving relationships of triangles. So I'll set up a poll for this, just like we did the last one. Every equilateral triangle is isosceles, and all acute triangles are equilateral. Like I said, I'll set up a poll for this one just like the last one. Same approach as before. Can I find a counterexample? If I can find a counterexample, then I'm going to say false. If I convince myself in my search for a counterexample that this has to be a true statement, then I'll just go with true. We aren't going to be doing any two-column proofs that where you write down step by step how you would prove something. But once you're convinced that something's true, you can say true. And I guess in some ways you're convincing yourself, well, I can't find a way to show this false, so I'm going with true. That's kind of what we're doing. But it's valid to do things that way. It's okay, to say, you know what, I'm convinced. I'm going with true. Let's go another 20 seconds on this one, and then we'll talk about them together. All right, let's see how we did here. Oh, unanimous, outstanding, very good. So I think the whole find a counterexample, the whole philosophy of how to go about attacking a true or false question must be doing pretty good. So that's great, because I don't think, true false feels like it should be easy. They're not always easy. All right, let's take a look here. Every equilateral triangle is isosceles. So I'm going to see if I can draw an equilateral triangle that's not isosceles. So I'm going to draw myself an equilateral triangle. All three sides are the same. Well, to be isosceles, I just need at least two sides the same. And as I look at this triangle, I can see, well, those two sides are the same, so it's isosceles. All right, well, I may be convinced, but let's just say I'm not convinced yet, and I draw a bigger equilateral triangle. with all three sides the same length, because that's what equilateral means. Isosceles, I just need two sides the same length. Well, I've got at least two sides the same length. Sure enough, that's isosceles. So every equilateral is isosceles. Every time I draw an equilateral triangle, it's going to be isosceles. So this is true. All acute triangles are equilateral. So what I want to try to do here is draw an acute triangle that is not an equilateral. Well, I kind of saw a picture of that just a minute ago. All those are less than 90, but it's definitely not equilateral. So every single one, no exceptions, all acute triangles are equilateral? No, that's not true. Right here's my counterexample. So I can go ahead and say false. If we were to reverse that, if we were to reverse this one and say all equilateral triangles are acute, well, the equilateral triangle's got to have 60-degree angles in it. So then that would be a true statement. But the way this one was written, all acute triangles are equilateral, that's definitely false. Let me know if you have any questions on any of that. Great job on that one. I don't think those are easy. Very good. Okay, the triangle inequality. This isn't going to be a big topic for our class, but it's something I want you to be aware of, and it makes for a cool experiment if you're in a classroom setting. What the triangle inequality says is, in order for a triangle to be drawn, the sum of any two sides must be larger than the measure of the third side. It's a little hard to digest that all at once, but the sum of any two sides must be larger than the measure of the third side. Essentially, what this is saying is that if we take the two smallest sides and add them together, that it has to be greater than the largest side. Obviously, if we, add the two largest together, it's going to be bigger than the other one. But the two smallest added together has to be bigger than the largest, or we can't make a triangle. This works, just sort of an example of that. Let's say we try to draw a triangle with side lengths 2, 4, and 11. According to the triangle inequality, this isn't going to work because 2 and 4 would be 6. That's not bigger than 11, so it's not going to work. And I'm just making sketches, so you kind of have to trust me on this. But if I try to draw a triangle with a side length of 2 and a side length of 11, when I draw this 4, it's not going to get there. It's not going to make it. And I should make it a little bigger. But, if I use 2, 4, and 11, that's what's going to happen. It's not going to connect right. It's not going to make a triangle for me. You could say, well, I don't know. I'm not sure how you drew that one. All right, well, what if I keep my 11 down here on the bottom and I do my 4 like this, and then I do my 2? Well, I made a triangle, but the side lengths aren't 4, 2, and 11 because the 11 ends up all the way over here. So trying to use side lengths 2, 4, and 11 won't work. Beautiful way to do this with a classroom to kind of show that it's true is to just cut string of different lengths. And they'll find out pretty quickly that, hey, wait a minute, if the two small ones don't add up to be bigger than the third one, than the biggest one, then I can't make a triangle out of this. They don't connect right. It won't be a huge topic in our class, but it's something I want you to be aware of, and I think it makes for a fun experiment. Okay, now we're going to talk about finding the sum of the interior angles of a regular polygon. Before we can use this word regular, though, we have to define it. Regular means that all the side lengths are the same and all the angles are the same. We've seen that so far. If we talk about a square, all 4 sides are the same, all 4 angles are the same. That would be a regular quadrilateral. We've also seen it here with the equilateral triangle. All the side lengths are the same, all the angles are the same. That would be a regular triangle. So that's what regular will mean for us. What we're going to do is we are going to work on a way of finding the sum of all of the interior angles of a regular polygon. So it's all the angles that are on the inside. And I kind of just drew those two right there. We drew a triangle. And a regular triangle would be equilateral. It would have three sides. It would have three angles. What would those angles add up to in a triangle? And I know y'all told me just a couple minutes ago, but I'm going to ask again. Perfect. Thanks, Summer. Shelby, Nadine, that's great. So that would be 180 degrees, would be the sum of the interior angles. So the sum of the interior angles for a triangle will be 180. And if we did a quadrilateral, it would have four sides. What would those angles add up to? We haven't mentioned this yet, but given that, we've talked about rectangles and we've talked about squares, I think you could figure out what the sum of the angles of a quadrilateral would be. Very good, Shelby, Summer, excellent, 360. Well, all right, wait. I love that you both put question marks on there because that sets this up perfectly for me. We're all pretty comfortable with the idea that if we add up the three angles of a triangle, we get 180. And if we have a quadrilateral, then where does the 360 come from? I mean, I get it when it's a rectangle, but what if it's not a rectangle? What if it's instead a parallelogram? And now they're not all 90. So I don't know what these angle measures are. Well, here's how we can get that it has to be 360. If I draw a line through here called a diagonal, goes from one side to the other, and it connects one vertex to another, and it goes through the middle of the polygon. That's called a diagonal. What I've created now is I've created a triangle over here. So these angles add up to 180. And I've also created a triangle over here so that these angles add up to 180. And so if I go back into this thing and I add up all of these angles, I've got 180 in this triangle, I've got 180 in this triangle, so sure enough, I have 360 altogether. Let me know if you have questions about that, or if it's uncomfortable. Up next, I want to look at a pentagon. We haven't spent a lot of time with pentagons, but a regular pentagon would look like this. My picture probably won't be perfect. Yeah, it's not. But imagine all those side lengths are the same. There's our regular pentagon. It has 5 sides, and I want to know what the sum of the interior angles of that would be. Gosh, well, I cut that rectangle up into triangles. Let's see if we can do that here. If I want to cut this pentagon into triangles, then I wind up with one triangle here, another triangle here, and then a third triangle that's right here in the middle. So I have 3 triangles in there. So let's see, I have 3 triangles. So you tell me if you're not sure where this came from, but I've got a 540 right there. How'd you get 540, Shelby? Oh, all right. That's a really interesting approach. So, right, we've got a quadrilateral in there that's 360. Throw on the extra triangle, that's 180 more. Anybody get 540 and get it a different way? All right, sunshine, great. 180 times 3. I've got 1, 2, 3 triangles in there. The triangles angles add up to 180. If I do 3 times 180, that'll get me there. And we sure enough land at 540. You're both correct. one thing I want to do is take a step back here for a minute. With a triangle, we have one triangle in there that we multiply by 180. With the quadrilateral, we had two triangles in there. We multiply by 180 to get 360. And now with our pentagon, I have 1, 2, 3 triangles in there. And if I do 3 times 180, that'll let me know the angles that are in the, if I add up all of these interior angles in my pentagon, then it has to be 540. And that's just the truth. All right, so there's a couple of things I want to try to do here then. I want to try to build a formula. And what I want you to do as we build this formula, and I'm maybe giving you more than you need, I apologize if that's true, but I want you to look at the side lengths and how we figure out how many angles there are. And if I just have an n-gon that has n sides in it, what would I do over here to figure out the angle measures of that n-gon? If you get this, that's great. If you don't, it's okay. Abstractions like this are pretty hard. All right, let's see what Sunshine's got there. All right, 180 times n minus 2. All right, so it's fantastic, Sunshine. You're exactly right. So what she did here was this. She said, well, when there were 3 sides, I did 1 times 180. When there were 4 sides, I did 2 times 180. When there were 5 sides, I did 3 times 180. So this number over here is always 2 less than the number of sides. So if I take the number of sides and subtract 2 and multiply that by 180, that's going to give me the sum of the interior angles of a regular polygon. And that's going to be the formula that we come up with here. The sum of the interior angles of a regular polygon is going to be found using this formula right here. N minus 2 times 180. And 180 times n minus 2 works just as well. So when we're asked for the sum of the interior angles of a regular polygon, that's the formula we're going to use to find it. Any questions on how we built that thing? Fantastic. Okay. So let's just say we were given a question that is, what is the measure of each interior angle of a regular hexagon? Wait a minute now, each interior angle, we didn't do that. We just found the sum of them all. Well, that's okay. We know it's regular, so we know they're all the same as each other. Okay, so this is a regular hexagon. Again, my drawing won't be perfect. It's okay. It's just a sketch. There's my regular hexagon. Hexagon has 6 sides, which means it has 6 angles. And what I want to know is if I have a regular hexagon here, how big is each one of those angles? That's the question we're being asked. Well, I can find the sum of the interior angles by using the formula n minus 2 times 180, which here, well, let's see, n is going to be 6 because it's a hexagon. So the sum of the interior angles is going to be 6 minus 2 times 180, or 4 times 180, which is 720. Let me know if you see anything that doesn't make sense or you're not sure where it came from. So what I just found is that the sum of the interior angles of this regular hexagon is 720. I'm not done though, because what this question asked me for, and you want to be careful with this, make sure you answer the question that's being asked. What it asked me for is what's the measure of each interior angle, so just one of them. Well, if I know they add up to 720, and I know they're all the same, and I know there's 6 of them, we just need to do 720 divided by 6. And so the sum, or excuse me, the measure of each of those interior angles has to be 120 degrees. Understanding all the words that are involved in this problem is what makes it possible for us to do it. You know, knowing that it's regular means they're all the same. Knowing that I can find the what I get if I add them all together by using this formula gets me here. And then, okay, it's a hexagon, so there's 6 of them. If they all have to be the same, I'll just divide to find out the measure of each one. Let me know if you have any questions on that before I have you try one. Outstanding. Okay, here goes. What is the measure of each interior angle of a regular 9-gon? I'll make a poll for this and let you try it. This is one of those fun questions for me because if I would have asked it in, about an hour ago and just said, what's the measure of the interior angle of a regular 9-gon? I imagine there'd be a lot of blank looks. I can't see you, but a lot of blank looks like, what the heck? And now it's one that I can throw out there in a poll. Let's see how we did on this one. And everybody solves it correctly. So it's pretty cool when there's a question. If you were just kind of read this out of the blue, there's a whole lot of language in there. It's relatively fairly complicated language. And now we're in a place where it's very comfortable and it makes perfect sense. So we want the sum of the measure of each interior angle of a regular 9-gon. Well, I can find the sum of all the interior angles by just using n minus 2 times 180. And in this case, because I have a 9-gon, I know that n is going to equal 9. And so when I plug that in, I'll have 9 minus 2 times 180, which will be 7 times 180 is 1,260. It's not my answer, it's a really important number. That's the sum of all of them. And since it's a 9-gon, I know there are 9 of them, so I'll do 1260 divided by 9. And sure enough, 140 degrees is the measure of each interior angle of a regular 9-gon. 9-gon would be hard to draw. One thing I can say, though, is if we were to draw a 9-gon and cut it up into triangles, there'd be 7 triangles in there. And that's why this formula works the way that it does. That one went great. Feels like everything from today has gone great. Anybody have questions they want to ask about anything we've talked about? Simple, closed, polygons, concave, convex, quadrilaterals, triangles, and then sum of the interior angles. A lot of different topics.